Hi, I'm Ivan Kelly from Streamlio, and at Streamlio we work on a system called Apache Pulsar, which is what I'm going to be talking about today. So I'll lead off with a quote. It's from Peter Norvig at Google, but there's a couple of versions of this quote going around from numerous different people. We don't have better algorithms than anyone else, we just have more data. And the reason there's multiple versions of it going around is because it's very true. If you have a lot of data, you will be forgiven for making mistakes in your choices of algorithms or the parameters you put into your algorithms. And this is particularly true in cases where rare events have a disproportionate impact on the final output of your algorithm or your model. So a good example of this is web search. So when you're crawling the web, if you come across a link for the very first time, that's going to have a much larger impact on the final index than if you came across a link that you'd seen a million times before. And the real world is full of data which has this kind of Zipf-ian pattern where you have a lot of very rare events, and then you have some events, a few events that happen very regularly. So I'm going to be talking about this in the context of streaming. So nobody's doing batch anymore, really, so it makes more sense. And in a streaming system, this is usually what the workflow looks like. You have a user. The user doesn't necessarily have to be a human. It can be like IoT devices sitting around outside somewhere, or it can be a user. The user generates events. These events get put into a messaging system or streaming system. They get fed from the streaming system into a stream processing system where the algorithms live. This generates a model. The model then gets put into some kind of serving system, and that gets given to the user, which then generates more events, and you get this kind of cycle. No, go back. So a more concrete example of this would be something like Spotify. So on Spotify, you're sitting at your desk all day listening to music, and that's generating events that gets fed into some kind of event bus that they have. These events then get fed into a recommendation algorithm, which is in some stream processing engine. This generates a user listening model, and then you end up getting recommended songs, such as you have your daily mixes or whatever. So this kind of architecture, where everything is a stream, is called a Kappa architecture. It's important to note that once data goes through this system, it can't just be discarded. You have a whole team of data scientists working to improve your algorithms to get better engagement from your customers and increase your company revenue, etc. And when they do make an improvement, they need to be able to test if it will actually do something good. And if it does do something good, you need to replay historic data against this new algorithm to provide the new results to the users. And you have to include historic data as well, because let's say we have a system such as this, where it's song recommendations. If you've been listening to Led Zeppelin for 10 years, you don't want them to completely discount that. So as I said, this is a Kappa architecture, but this isn't how things normally end up. You normally end up with something like this, which is called a Lambda architecture. And in this case, you have two sources of events. You have the historical events stored in something like HDFS or S3, and then you have live events in something like Kafka. Now, the reason it ends up like this is because traditionally messaging systems are not able to store massive amount of data. For example, with Kafka, if you have a topic or a partition, the maximum amount of data that you can have in that partition is the maximum amount that would fit on the broker on the disks of the broker, which is hosting that which that topic is assigned to. So you end up with something like this. You have two parallel streams of data, which means you also need to build two pipelines. You need a batch pipeline and a stream processing pipeline. These need to create partial models, and then you get a combined model, which then goes to your serving system. And obviously, this is not ideal. If you have two pipelines, you have two sets of systems that you need to maintain. You have whoever's developing your algorithms needs to write that algorithm for both systems, and it's just a lot of overhead. So what would be really nice would be to have a true Kappa architecture. And that's what this talk is about. So with Apache Pulsar, you can get rid of the historical data pipeline and store everything in a single stream, because with Pulsar you can scale, your streams can grow forever. So I'm going to talk about how we scale our streams like infinitely. I'm going to talk about how you can move older parts of that stream into some long-term storage without losing the flexibility of being able to access it through the same APIs. And also, finally, I'm going to talk about our SQL layer. So if you have this massive backlog, you don't want to have to be writing code every time you want to get some kind of answer out of it. So we provide an SQL layer, which I'll talk briefly about at the end. So just to briefly introduce Apache Pulsar. It's a messaging system, pub, sub, and queuing semantics, strong guarantees on message persistence. I'm basically reading this out. It started in Yahoo maybe about 4 years ago. It was kind of the end of a result of a long journey. So I was working for Yahoo back in 2010 was when I started. And at that stage, Yahoo had this massive globally distributed database called Sherpa. I think publicly the name is Peanuts. There's an academic paper on it. And Sherpa was using a system based on NetApp filers to store the write-ahead log of the tablets and distribute that to the different colos around the world. And they'd been trying to get rid of this system for years. So the first thing I worked on Yahoo was a system called Hedwig, which looked very similar to Apache Pulsar, but it died for political reasons within the company. It did get open sourced as well, but then it kind of got thrown in the attic. After that, there was another system based on RabbitMQ, which had Bookkeeper as the underlying storage layer. That didn't really work for the Sherpa use case. The brokers just weren't able to keep up. And Kafka was also considered, but given the number of topics needed, it just was a non-runner. So eventually, 4 years ago, they started to write Pulsar. And because we had this long, I'd already left the company. I was just about to leave the company when Pulsar started. Because we had this long history of trying to build and fail for the write-ahead log, we learned a lot of stuff before Pulsar was made, and that got put into Pulsar, and it meant we could build stuff into it from the start, which would be very difficult to add later on, stuff like multi-tenancy and geo-replication, this kind of stuff. But I'm not really going to talk about that today. I'm going to talk about the unlimited backlog size, how we achieve that. I'm going to talk about tiered storage, which is how we allow data to be moved onto cheaper storage. And also I'm going to talk about the SQL interface. So just to give an overview of what a topic backlog is. So in some message brokers where you don't have any persistence, you publish to the broker, and if a subscriber is attached to the broker at that time, they will get that message. But if they're not attached, they won't get the message, or if they drop, they mightn't get the message. You lose all kinds of reliability there. So to avoid losing messages, most messaging systems will have something called a topic backlog, which is like a log of the messages that are written to the disk. Oh, sorry, to the topic or the partition, depending on your terminology. So client produces a message. This message is written into a log. It's on disk, but it's not necessarily on a single disk. And then the broker doesn't acknowledge the message until it knows it has been, well, in Pulsar, it doesn't acknowledge a message until it knows it has actually hit hardware. So we actually guarantee that we do an fsync. And so on and so forth. Yeah, no, go back. So the way Pulsar does this, we give strong guarantees on the ordering of messages. So if we have told a client that message E has been persisted after message D, then that is the order that all clients will see these messages. They'll see them in order, without duplication, without any drop messages. And it's a property called total order atomic broadcast. And it's a very nice property to have in your system because it means you can build other stuff on top of it. So the backlog in Pulsar it's broken into segments. There's two kinds of segments. You have closed segments and open segments. So the closed ones are the pink ones in the diagram, and the open one is the green one. An open segment is the current segment that you're writing to. If once a segment is closed, then you can't write anything to it. It becomes immutable for all time. So the only way, in this case, if you need to delete any messages from a segment, you actually just have to delete the whole segment. Like, usually your deletions are based on something like a retention policy, which you can set your retention to infinite, where it keeps everything, or you can set your retention based on size or based on time. Segments are, well, they're immutable, but they also act completely independent of each other in Pulsar. So if one segment, like, they don't share any properties, they don't necessarily share any properties, but Pulsar does know the order of segments. So Pulsar does keep, for each topic, it'll keep a metadata, which is basically a list of all the segments that contains messages. And obviously the order in that list of the segments can never change. So one property of having the segments being completely independent is that each segment can have its own replication specification. So let's say this segment is being replicated to storage node 1, 2, and 3. There's nothing to say that the next segment couldn't be replicated to storage node 4, 5, and 6. And this is kind of where we get the infinite backlog. So because we don't have any, because the segment isn't tied to any single set of nodes, we can just keep adding nodes to add more segments to the topic backlog. So Pulsar is built with what we call what do we call it actually? I can't remember. We separate the storage and the serving layer. So the storage layer is Apache Bookkeeper, which is a much older project actually. That's been going for 10 years now, I'd say. And the serving layer is Pulsar. So Pulsar is kind of like it's a stateless broker that adds all the enterprise niceties on top of like the interesting replicated logging stuff of Bookkeeper. Separating the serving layer and the storage layer like this makes it really easy to scale your system depending on different requirements. So let's say you have a lot of subscribers for your topics. The bottleneck there will be network throughput. So the way to scale up your network throughput would be to add more brokers to your configuration. However, if you have a case where you've a moderate or small number of subscribers, but you have a lot of publishers writing messages, and these need to be persisted for a long time. In that case, you increase the number of storage nodes. And as you add a storage node, the storage capacity of your system goes up. And there's also a nice feature in Bookkeeper where we allow, within a single segment, or we call it a ledger in Bookkeeper, you can stripe across multiple nodes. So if you want to increase your storage throughput, you change the replication specification to, let's say, have 6 storage nodes, whereas with each entry only being required to be acknowledged on 3, and then your throughput increases. So how we add a node to a cluster looks like this, a storage node to a cluster. So you have your topic backlog, and these segments are replicated on these 2 storage nodes. And eventually you see that your storage is getting a bit too full, so you add another storage node. Pulsar will recognize that a new storage node has come up, and it will gradually start to move, not move, but to write new segments to this node. So there's no rebalance here. As you add a storage node, it gets used automatically by the system. So to have am I at the last slide there? To have an infinite amount of infinite backlog for your topics, you just need to keep adding storage nodes. But this is not ideal for a number of reasons. So first of all, if you keep adding storage nodes just to get more storage capacity, you're still paying for the CPU and the memory of the physical machine that is storing that data, even though that data may not actually be used for in the next 2 months, even once. And it's also, from a storage point of view, it's more expensive than it needs to be. So in the previous example, we were doing 2x replication, which means that the copy of the data is written on 2 nodes for redundancy. So one of the nodes can crash, you still have your data. This is quite inefficient. So it's called mirroring, and it has a space efficiency of 1 over n, n being the number of replicas that you write. And this is to tolerate n minus 1 failures. But in reality, often you only need to tolerate 1 failure, because if you have a system that one of the nodes fails, you should be able to recognize that one has failed and bring the data back up to the number of required replicas. And this gets much worse as you add more replicas. So if you had 3 replicas, you would have like 1/3 space efficiency. And there are algorithms and schemes which do much better than this. So the one people would be most familiar with would be like RAID 5 or RAID 6. And in this case, you have, in this case, each block of data is only written to a single node, or disk, as in the case of RAID. And then the data is, a parity block is generated. So parity is like, for all bits at this position, ensure that the parity bit makes them sum to an even number or something like this. And this is much more efficient than mirroring. So striping with parity, you get 1 minus 1 over n space efficiency, which means that space efficiency will increase as you add nodes to your system. And in this case, we tolerate 1 failure. You can also have, I think RAID 6 tolerates 2 failures by adding another parity disk. But this isn't a free lunch. So the problem here is, if you do have a failure, it's expensive to regenerate the block that was lost. So you can store some of your backlog like this, but you can't store it all. So you can save a lot of money by storing the older part of your backlog like this, but it doesn't make sense to actually store your open segment like this, because if you were to do that, you would have to wait for the block to fill up, for multiple blocks to fill up before you could stripe them across. But you cannot acknowledge a message has been written until it has actually hit disk, so your latency on writes would just go to hell. But for closed segments, it is perfectly possible to store them like this, and you get a great saving. But we don't actually implement this ourselves. We actually use someone else's implementation. And this is our feature called tiered storage. So we have a long-term store, so it can be HDFS or actually HDFS isn't implemented, but it can be S3 or Google Cloud Storage. And it works like this. So you start adding messages to your topic. Your backlog starts to grow on these storage nodes. Eventually, you're going to hit a threshold where your nodes are, again, starting to run out of disk. And it will start to move data over. There's two kinds of thresholds, actually, you can have. You can have a time-based threshold, which is like move everything older than 2 days to long-term storage. Or you can also have a size-based threshold. So say if you go past 10 gigabytes in a single topic, move it off to long-term storage. There's also manual triggering also. For the client, this is absolutely transparent. So a client doesn't know if the data they're reading or consuming is coming from the long-term storage or I want to say, well, it's not quite local storage because it's stored on a bookkeeper, which is still a distributed system, but it's local to the Pulsar cluster. Next. Come on. There we go. So the offload process works like this. So as I said previously, Pulsar keeps a metadata on each topic, which includes a list of segments. And each entry of the segment, the entry for each segment points to where that segment lives. So the first thing we do when we're offloading is we update the entry for the segment that's being offloaded, and we write the potential location that we're going to write it to. The reason we do this is that usually when you're writing a segment, you're talking about a couple of gigs of data. If you fail after having started writing the segment, you could end up just having orphan data on S3 or whatever, and you're going to be charged for that forever because if it's orphan, you've no handle to it. So we write the potential location, and then we start copying all the messages over one by one. Oh, well, not one by one, we do it in batches and try and be as efficient as we can. While we're copying the messages over, we keep track of where these messages are in the offset within the blob. And then once we have all the messages copied over, we take these offsets, build an index, and then set the offloaded status of in the Pulsar metadata to true. The reason we have an index is if you want to start reading from halfway through a segment, as often happens when you're reading a backlog, you don't want to have to read the whole prefix. But equally, we could have actually just got rid of the index, because usually when you're reading that much data, the amount of data that you would read unnecessarily is quite low. And so finally, once we have the segment marked as offloaded, we delete the original data. This is a lazy process. So what happens when, we have a grace period before actually marking the ledger and bookkeeper as deleted. And then once you mark the ledger and bookkeeper as deleted, it doesn't actually get deleted until bookkeeper runs garbage collection. Not Java garbage collection, but its own garbage collection algorithm. So tiered storage, well, it's been available in Pulsar since version 2.1, which was last, oh geez, no, it's almost 2 years it's been in there now. We have a offloader for Amazon S3. We have one for Google Cloud Storage. We have written one for Microsoft Azure and Hadoop, but these haven't been merged yet, and the effort seems to have died down on to actually get them merged as well. So, but if there is like requests for them, they will get done fairly soon. Okay, so I'm going to do a demo now of the infinite backlog. It's not an infinite backlog, it's not quite that big, it's about 10 gigs, but I'm just going to show you how you can replay stuff based on large backlog size. So the demo, we have a Twitter topic, which is coming from Firehose. I think that's publishing about 50 messages a second or something like that. This gets fed into a function which is being hosted in the lightweight compute on Pulsar. And the function is a min count sketch function. If you're not familiar with min count, it's a way of counting things in sublinear space based with a large dictionary. So in this case, we're going to be counting the most common hashtags that we're seeing on Firehose. And then we also have two other topics. We have a query topic. The messages in this they don't have any actual content. They're just a trigger for the min count function to dump the result into another topic, the result topic. Okay, now hopefully this works. Last time I tried it at a conference, it all blew up. So there's this little query application. So, and this is showing what the top 10 hashtags are. Where's my mouse? Oh no, it's on the other side. So here we have, okay, this is one run, and it's Boris Johnson, Brexit, and a whole load of, well, I think that's Japanese and some Chinese there as well. But I run it again, and it's completely changed. Now, you wouldn't expect this to happen if you are actually doing counting stuff well. Like, you would expect it to be pretty stable between, within an hour time frame. So let's look at the actual code and see what it's doing. And that's the query code. Okay, so this is the function that we are running. So it takes in a record, and it either returns null or the top the top 10 hashtags if you get a query input. But, okay, so here's the problem. The problem is that the min sketch matrix was only a 1x1 matrix, so it didn't do anything interesting. So I'll increase it to 1,000. Wait, let's just look at the backlog quickly. So currently we have oh no, that's the wrong one. So this is the actual backlog here. We have a whole bunch of ledgers. Most of them are marked as offloaded. A couple at the end are not offloaded. I think there's only one at the end. And if we want to see how much data is in it, so this offloaded, there's about 10 gigabytes that this works out to. And the non-offloaded, you have about... Okay, so this is a quirk in Pulsar. The current ledger that's been written to, it doesn't report the size because it doesn't have that size within the metadata yet. So let's try again with our query, with our algorithm, and redeploy it using using a larger matrix size for the count min sketch. So we want to delete the function. We want to create it again. This can take a couple of seconds because it's a pretty puny cluster I'm using. Oh, come on. Okay. Oh, come on. Curse of the demo. Let's try it again. Right, let me just check the logs, see what it's doing. Whoa. Oh, because I have all the debug logging on as well, so. No. This was working this morning. I'll give it one more go, and if it doesn't work, I'm going to move on. So anyways, what you would see would be that the function gets recreated, the backlog starts getting fed into the function, but it's starting with the current backlog because you recreated it, starting at the end of the backlog. So then you can reset your cursor. Oh, no joy. So you can reset your cursor to start reading the backlog from a long time ago, and well, so you can set it back to a week or from the very start. And the results you get then when you rerun the query will be, it basically won't change by very much. It's actually mostly, I think it's hashtag BTS. It's like the fire hoses give me a strange segment of the data. Let me just try it one more time. Okay, I'll move on while that's going on anyways. Finally, I'm going to talk about the SQL interface provided by Pulsar. So it's basically a PrestoDB implementation of a Pulsar backend. It's been available since version 2.2. And it uses a lot of the schema stuff that we built into the messaging system to actually provide a table-like interface. I'll show you this in a demo in a minute, assuming this part of it works. One important thing to note is that the Pulsar SQL implementation is for querying data at rest. So there are some streaming systems that query like live topics. So you write a query, and if a message coming in matches that query, that's presented to you somehow. This is not what Pulsar SQL does. Pulsar SQL is for data that is already solidly in your backlog, and it gives you a definite answer. You know, there's an end on it. It doesn't keep streaming new results to you as you write it, as messages are being written. So the deployment model is very similar to well, any Presto deployment model. You have a coordinator, and you have a whole load of Presto worker nodes. And these don't actually go to the broker for the backlog. If we went to the broker when you're doing a single Presto query, usually with Presto, when you do a query, you end up having to pull all the data in the query to the workers before you actually do anything with it, and this would collapse your brokers if you're actually using them for any live traffic. So what Presto does is it goes directly to the storage, which is designed to be able to take a heavy read workload at the same time as a live write workload from the real-time traffic. And it can also go to, well, in this case, S3, because it uses the same interface for the storage as the broker does. Okay, so now I'm going to try a demo of this and hope it works. I'm going to try this while I'm in the other window. Okay, so this clock is in the way. So the first thing you can, so by listing the schemas in the Pulsar driver, you can see the different namespaces that are available. So this is a topic namespace. Public default is a default one that exists in Pulsar. Public offloaded is the one I've created. All the data in that is offloaded to S3. And then you also have some system namespaces for internal stuff. So let's list the tables within the offloaded. So I actually have two tables in the offloaded. So I have the faux-bar table. Well, I don't actually know what faux-bar topic is. Twitter raw, which is the raw data coming in from Firehose, and Twitter cleaned, which is that data with the there's lots of junk in there where messages get deleted. I don't want that in the data I was using for the count min sketch, so I just removed it. So you can describe one of these topics or tables, and you'll get the schema that is being used within. So there's a lot of stuff in this schema because it basically flattens all the what's the word, the non-simple structures, and it infers the types and all of this kind of thing. So with this, it's quite easy to write a query. You also get some built-in stuff that isn't part of the schema. These are all the underscore stuff, like the partition it's in, the time the event occurred, the message ID. Usually you won't need to use these, but they're there if you do. So let's actually write a query. So select username and text. I'm just going to select 10 of them because, as I said, it's a very small cluster. There's only two workers. And there we have, it's not displaying very nicely because of the size of the screen. But can you read that? So yeah, it just works like a basic SQL interface. You can connect to it through an API as well. And it allows you to make queries on your massive backlogs without having to write code, which is pretty nifty. Let's just go back and see if, oh no, I don't want to do that. Did this actually work in the end? No, it didn't. Okay, so that's the demo I won't do again. Okay, so, oh no, I need to change window. Yeah, so with that I'm going to wrap it up. So the takeaway points are Apache Pulsar allows you to have unlimited backlog size. You can offload the older data to a cheaper storage, saves yourself a lot of money. And we also provide a query interface that allows you to look into all this data without having to break out your compiler. The use case I motivated this with at start was a recommender system type use case, but there's a lot of other kind of use cases where being able to retain your backlog forever is really, really useful, such as CQRS, event sourcing, etc. So the important point is with Apache Pulsar, this is actually all possible. Okay, thank you.
Thank you, Ivan. Let's get to some Q&A. We've got a few questions. First off, if you had to tell one feature to move someone from Kafka to Pulsar, what would it be?
Tiered storage. Like, you get a massive financial win by not having to spin up disks for all your backlogs. So if there was one feature, it would definitely be tiered storage.
Okay. Do you have a second feature?
Not really a feature, but it's the architectural separation between storage and serving. It's the kind of thing that makes tiered storage, tiered storage was actually very simple to implement. Whereas if we didn't have that architecture, we wouldn't be able to have the system. So, it's yeah.
Okay. Is the only real difference between Kafka and Pulsar the separation of the service and storage layers so it can theoretically scale infinitely?
Well, there's a lot of real differences. They're completely different code bases, and they fit into the same ecological niche. So there's a lot of similarities, but there is stuff in Pulsar that I think would be very hard to do well in Kafka now because they weren't done from the start. Stuff like, as I said at the start, geo-replication. People use Mirror Maker, but I've never heard a good thing about it. The other one is real multi-tenancy. So you can have multiple tenants in Kafka, but there's no kind of namespacing of the different topics, so ACLs get a bit more complicated. With Pulsar, you have tenants, namespaces, and then topics, and it allows you to give quite fine-grained control to teams within your organization, this is why it exists, because there's many, many different teams within Yahoo who are using Pulsar, and they needed to make sure that they were kind of walled off from each other from the very start. So yeah, there's a lot of real differences. But I can't just list them off off the top of my head. So
fair enough. Okay. Does Pulsar reuse some protocol or code base from Kafka?
No. Technically there is. So we implement the Kafka API in in kind of a drop-in jar. So if you're using the Kafka API, you can depend on our jar instead, and you can use it as if it's Kafka. But that's the only Kafka code in that code base right now. At Streamlio, we have actually written a compatibility layer, like a wire compatibility layer, so you can just use your stock Kafka client with with a Pulsar cluster. We released the code there last week. It's still pretty beta, but it works. And that does bring in some Kafka code. But Pulsar was built from scratch without taking anything from them, really.
Okay.
In fact, if you look the other way, they took some ideas from Pulsar, like storing the offsets in an actual topic.
Oh, okay.
Yeah.
Good to know. Is there any Kafka compatibility on API level? A lot of things can wipe to Kafka.
I guess that's right, but yeah.
You would know better than I.
Yeah, as I just said, there's a wire compatible messaging gateway, and we also have a drop-in jar for kind of a poor man's API compatibility.
Okay. Why add a storage layer if we could directly write into a long-term storage? Isn't it inefficient to have storage nodes copying data into the long storage?
So you want to write to the messaging system first because you want to get the ability to kind of broadcast your data. So instead of everyone writing to a slab a blob of data into, say, S3, and then everyone who's consuming that data have to wait for that block to be written. With a messaging system, you write it to the topic, and it's available straight away. Or maybe this question is asking, why do we have Bookkeeper? You can't actually do... One of the properties that Pulsar is built on is total order atomic broadcast. You can't actually do that with S3. You can kind of do it with HDFS, but it would be super slow, and it would follow. You'd bring down your name node pretty quickly, because every time you f-sync, that's a write back to the name node, which isn't good.
Okay, well, that's all the time we have. Thank you so much on behalf of the conference for your time and for being here with us. And I just want to say that Ivan will be here for office hours in the Prezi booth, which is behind the information booth in the sponsors hall. But he does have a clear deadline, so if you want to talk to him more, make sure you get there in the next 20 minutes.
Yeah.
Thank you.
Thank you.